Okay, so welcome back. This is part two of the lecture, and this should be a lot shorter than the first half. But I thought it would be better to talk about z-scores in its own file or its own video, so that you might be able to refer back to this specific video in lectures that we're going to complete in the future. So this is just going to be an introduction to z-scores, also referred to as standardized scores, and again, an introduction because we're going to be working with these a lot during this semester. So we'll start slowly. And today, or with this lecture, I just want to introduce the concept and let you know how z-scores are calculated. So a z-score is the number of standard deviations. The actual score, or what we would call a raw score, how many standard deviations that score is above the mean if the score is positive, or below the mean if the score is negative. So we're able to take, once we have a mean and a standard deviation, we're able to take any score that exists within that distribution and determine how far away is that score from the mean. We can do that by computing a z-score. So z-scores are helpful in that regard. Z-scores are also helpful because they allow us to compare individual scores on a standardized scale. So you might have heard this term standardized scores before, or standardized testing before. You might be familiar with the idea of curving a grade or curving an exam, right? That's not always in the best interest of students. We'll see why in a moment here. But if a professor were to curve their grades or curve the grades for an exam, essentially what they will do is calculate the mean, calculate the standard deviation, then convert everybody's score into a z-score, and then essentially assign grades based on that standardized score and based on some type of standardized criteria for what constitutes an A and a B and a C and so on and so forth. So some examples of standardized tests that you may be familiar with are SATs, the ACT. If you're going to apply for graduate programs, you're likely to take the GRE, which is also a standardized exam. So let's dig into that meaning a little bit more. What are we actually talking about when it comes to standardized scores? Well, it's a way, again, to convert any type of data or any type of continuous data. If you have a mean and a standard deviation, you're able to convert your data set or your distribution into a standard distribution. You're able to calculate z-scores. So z-scores allow us to compare scores that are obtained from different scales of measurement. So we can take SAT scores and GRE scores GPA scores, and you might say, well, one's apples, the other's oranges. So how are we going to compare these two? Easy. We can standardize them, right? We could take those apples, we could take those oranges, and we could turn them both into bananas and then compare those scores directly. So z-scores are transformations of scores. They standardize them, or quote unquote normalize them, because you're able to convert these raw scores, these apples and these oranges, and you're able to plot those scores onto a normal distribution and compare those scores directly. So z-scores are pretty helpful, pretty useful here. As we're going to see in future lessons, z-scores are part of many statistical procedures that exist out there. The first hypothesis testing that we're going to do is going to involve z-scores on a normal distribution. Everything after that is going to be based off the same principles of a z-score and the same principles of a normal distribution, even though we might not necessarily be using z-scores or a normal distribution for almost all of these statistical tests that we're going to be doing in this class. We're going to be using variations of z-scores and the normal distribution. So it's important that we get a good understanding of what z-scores are all about. As I said, z-scores can be plotted on a normal distribution, and we've talked briefly about the normal distribution already, but just so you can have a visual idea of what we're talking about here. The normal distribution is a distribution that we see very, very often in the behavioral sciences. So this is a distribution that we deal with a lot as psychological researchers or behavioral scientists. We'll learn more about the normal distribution actually in the next lecture, so I don't want to get too ahead of ourselves at the moment here, but hopefully this shape is somewhat recognizable. You hopefully have seen this shape before, and you have an understanding of what it means. The normal distribution is a frequency distribution, or rather a frequency graph. It's a polygon, right? This line represents frequencies. So it's a little more complicated in that regard, because the normal distribution, this perfect curve that we see here, is more of a theoretical distribution. If we were to collect a whole bunch of data and graph it, depending on what variable we're using, but if we were getting data on people's height or weight or IQ or attractiveness or happiness, almost you name it, endless number of variables that will take on this curve. If we were to get data, a lot of data on any of these variables that are of interest to behavioral or psychological scientists, it's likely that once we plot it, the data is going to take on this shape. And let's just take a look at this shape briefly for a moment here. So once we standardize scores, what we're doing is taking the mean of our distribution and we're going to transform that into 0. So this point of a normal distribution, this highest point, represents the mean, the median, and the mode in a normal distribution. So it kind of makes sense why it would represent the mode, right? Because if these are just frequencies, well, this is the score that occurs most often. So this is the score with the highest frequency. But through the process of standardizing scores, this score here will also equal the median. So if we were to draw a line up here, that means 50% of the scores on this graph or in our distribution are going to fall below 0, below this line, and 50% of our scores are going to fall above 0 or above that line if we drew a line from 0 straight up. So represents the mode, represents the median, and it's also the mathematical average of all of our scores in this distribution. So it's the mean, the median, and the mode. And this 1 here and this -1 on this side represents one standard deviation away from the mean. So +1 would be one standard deviation above the mean, and -1 would be 1 standard deviation below the mean. -2, 2 standard deviations below the mean. +2, 2 standard deviations above the mean, so on and so forth. So we're able to take any data out there, not any data, but almost any continuous data, any interval ratio data, and make it fit to this graph. We can do it. So it's pretty neat. Again, we'll be talking a lot more about this normal distribution. We're going to be talking a lot about it in the coming weeks. So this is just an introduction. So again, these scores here are z-scores, standardized scores. They also are standard deviations, right? So 0 standard deviations, that means you're 0 units, 0 values away from the mean, because that is the mean, and the median, and the mode, right? But once we get to this part of the graph, we're 1 standard deviation away from the mean. Once we get over to this part of the graph, we're 2 standard deviations away from the mean, so on and so forth. Okay, so how do we calculate z-scores? How do we calculate these standardized scores? You really just need 2 things, and we already know how to calculate those now. You need the mean, you need the standard deviation. Well, I guess 3 things. You also need a score that you want to standardize. So to transform a raw score, this is just your normal unstandardized value that exists in a distribution. You take that raw score, or that x score, and you subtract the mean. And from that score, or you subtract that mean from that score, and you divide by the standard deviation. So we have an x value, subtract out the mean, and divide by the standard deviation. So let's say we have, let's say you scored a 96 on the first exam. And that exam had a class mean of 78. So the mean for exam 1 was 78, and it had a standard deviation of 12. So on average, each score, deviated from the mean by 12 points. And you scored a 98. So let's see what your z-score would be, what your standardized score would be, if I were to quote-unquote curve this exam. And when students ask if professors are going to curve an exam, what they typically mean is, or what they're typically asking is, whether the professor is going to add extra points. But that's not curving an exam. Curving an exam is to take all of those scores and fit it to that normal distribution. So let's say I was actually going to do that. So how would we calculate your z-score? Well, we would take your 96. That's your raw score. That's what you earned. That's your x value. That's what you got on the exam. So we would subtract the mean of 78 from that, and we would divide that value by 12. So you would get a z-score of 1.5. Okay, so in this lecture, we're not plotting z-scores yet, but just keep this in mind. Your z-score would be 1.5. I'm just going to go back to our normal curve here. So if I were to plot it, which we're going to do in the next lecture or two, if 0 is here, right, that's the mean. That's would be our 78, the class average here. You got a 1.5, which means if I were to plot your score, you would end up right about here, right? So you would be 1.5 standard deviations above the mean for the class. That's pretty good. Not bad, right? And we know it's not bad because your raw score is a 98. And the class was, 78, if I'm remembering correctly. Sorry, you were a 96 and the class was a 78. So, you're 1.5 standard deviations above the mean. So, you're a pretty good distance away from the mean, which means that, you did fairly well on this exam. You're out there on that normal distribution. Okay, so, we could also take a z-score and transform it back into a raw score if we know the mean and the standard deviation. So calculating calculating z-scores from raw scores is pretty easy. You remember, you would take your score, your raw score of x, subtract out the mean, divide by the standard deviation. That'll give you a z-score. Now, what happens when I have a z-score? Well, we just have to work backwards now, right? So let's say, here's the formula. You have a z-score and you want to convert it back to a raw score. So the raw score, or x, is going to equal the standardized score, or the z-score, times the standard deviation plus the mean. Okay, so this is just one of those formulas that you're going to have to remember or keep in your notes. Okay, so in our previous example, your z-score was a 1.5. The standard deviation for the exam was a 12, and the mean for the exam was a 78. So all we have to do is plug and chug at this point. So we plug in our z-score of 1.5, we plug in our standard deviation of 12, and we add the mean, and we end up with a 96, your raw score on the exam. So z-scores, again, are just transformations of scores. You're taking a raw score and you're calculating a standard deviation. What we're really asking by computing these z-scores is how far away from the mean are each of these scores in our distribution. So when you get a z-score of, say, a 1.5, you would know that you're 1.5 standard deviations above the mean. You might not know what the mean is. You might not know what the raw score for the standard deviation is, but a 1.5 away from the mean means, hey, I scored, even if we all scored really crap, we scored really horribly on this exam, I'm still in high level of the crap scores, right? If the mean were 50, and we had a standard deviation of 10, and you got a 1.5, I mean, you're still at a 65 in the class. And you might say, well, that's failing, but you're still 1.5 standard deviations above the average, the mean for the class. So z-scores help us visualize how far away each score is, let's say, from the mean. That'll make more sense once we actually start plotting z-scores on that normal distribution, once we calculate them and plot them. I just want to give you an introduction to what they do and how to calculate them. Okay, so let's take our original scores, our raw scores that we used in our example before. These are raw scores for an exam, I think they were. This is that distribution, that data set that we've been using throughout the part 1 of this lecture. So we're going to take all of these raw scores and convert them into z-scores. Essentially, we're going to convert them into standard deviations. So how do we do that? Well, remember what we found. The mean for this distribution was 79.55, and our standard deviation was a 17.15. Okay, so now that we have that information, all we have to do is remember the formula for taking a raw score and converting it into a z-score. And that formula is x, which is your raw score, minus the mean divided by the standard deviation. So in our case, we have our first raw score, which is 60. We'll subtract out the mean, which is 79.55, and divide by the standard deviation, which is 17.15. And this gives us a z-score of negative 1.14. So what does that z-score mean? It means that 60 is 1.14 standard deviations below the mean. So 60 is not a good score, right? It's pretty far away from where most of the classes in the opposite direction, in the wrong direction, in the negative direction, right? So having a z-score of 1.14, you know that you probably didn't do so great on this exam. Most people are going to score within one standard deviation above or below the mean, and you're past that, right? Below the mean, in the opposite direction. Okay, so we can just go ahead and fill in our z column here, and we're going to do this for each raw score. So we have a 62 next. 62 minus the mean divided by the standard deviation, and we get a raw score, or a z-score of negative 1.02. Still not great, right? We're still more than one standard deviation below the mean, so still not a great score. And we can do this for each one of our scores, just plug and chug. But take a look once we start getting into some of these higher scores, right? We get to see, a mean of 70, 79.55. That's almost an 80 in the class. But by the time you get to a 98 in the class, you're still over one standard deviation above the mean. You're doing great. You're doing better than most people, the majority of people in the class. And this is a pretty small data set here, just using this for as an example, just for illustrative purposes. Once we actually calculate these types of scores for larger data sets, and we start plotting them on a normal distribution, hopefully it'll start making more sense as to why we do this. And then hopefully that'll help you once we start talking about hypothesis testing. But I'm gonna do my best not to jump the gun here. So we'll be getting to that. Okay, so what if we were to add up all of these z-scores? What would we get? Well, let's add them up. We get 0, right? And we'll talk about why that's the case next time. But try thinking about it, right? Think about what z-scores are. Remember, they're standard deviations. So they're standardized. We're kind of running into the same issue that we ran into when we were trying to add up those deviation scores when we were trying to calculate standard deviation. We couldn't just add up those deviation scores because we got 0 when we added them. We had to square them. So just keep that in mind, and then think about why would we run into the same problem if we were trying to add up the z-scores in our distribution. And let your brain chew on that for a while, and then we'll talk about why that is the case. But we will do that next time. So for now, enjoy the rest of the week. Take care.